Hello everybody. In this video, we are going to talk about covalent bonds. If you remember, covalent bonds are bonds that are formed usually between nonmetal atoms. And in the bond, each atom shares 1, 2, or 3 electrons, as we'll see later. So, before we begin talking about the single, double, and triple bond, let's talk about what Lewis dot diagrams are and what Lewis structures are. A Lewis dot diagram simply shows the valence electrons surrounding an atom. So, for example, in this oxygen atom, I need to add 2 more electrons there. In this oxygen atom, the oxygen has 6 valence electrons since oxygen is 2s2 and 2p4, and that's 6 valence electrons. Meanwhile, something like nitrogen would have 5 valence electrons due to its electron configuration. And as you can see, each dot represents 1 valence electron, and we typically write the electrons in pairs before moving on to another pair. To see how I paired them up like this, well, that's what Lewis dot diagrams are. Now let's talk about what Lewis structures are. A Lewis structure is essentially the same thing as a Lewis dot diagram, except whenever you're dealing with a bond, or when 2 atoms share electrons, then the 2 electrons, 4 electrons, or 6 electrons that are shared are drawn as lines instead of electrons. And I'll show you how this works right now. So when we take a look at a single bond is where each atom contributes 1 valence electron to form a single bond. And as you can see, a single bond can be also written as this. And this line represents 2 electrons where each atom is contributing 1 valence electron to that bond. And this would be an example of a Lewis structure, while this would be a Lewis dot diagram. Now, you might be wondering, why do atoms make single, double, or triple bonds? Well, hydrogen has 1s1, and it wants a full valence shell. So, if another hydrogen atom pitches in to give it an extra electron, then this will become 1s2. And remember, for hydrogen and helium, 1s2 completes the valence electron shell, and that makes atoms stable. So if hydrogen is able to get 1s2, then it will be stable. And in this case, both hydrogens have 1s2 because each of them have essentially 2 electrons, which is all they need to fill their subshell, and that makes them stable. So by sharing electrons, both of these hydrogen atoms are able to be happy and stable. Now let's take a look at a double bond. A double bond forms when each atom contributes 2 electrons each to the bond. So over here in the Lewis dot diagram, these 2 oxygen atoms are donating 2 electrons each, which make 4 electrons in total. And this can also be written as 2 lines, where each line is 2 electrons. And this would be considered a double bond. Now, this electron here and this electron here are electrons that are not part of the bond, so they are called non-bonding electrons. And these 2 electrons that I circled are known as a lone pair, and that's because it's a pair of electrons and they're alone and they're not bonding. So there are 2 non-bonded electrons, and I don't know why this happened. It's supposed to just be 2 pairs of electrons there. So that's how a double bond works. Now a triple bond works in a very similar fashion. 2 nitrogen atoms in this example each contribute 3 electrons, so it's hard to see, but let's just say that the first nitrogen donated these 3 and the second nitrogen donated these 3. So that's what a triple bond is, and it can also be written like this. where each line or bond represents 2 electrons. So there are 3 lines and there are 6 electrons, and it's a triple bond. So let's now look at why atoms like oxygen and nitrogen want to bond. So for something like oxygen, let's write the valence electron configuration. Remember that unlike hydrogen, oxygen also has p electrons that it needs to fill in its valence orbital. So for something like hydrogen, the 1p orbital does not exist, and as a result, it only has to fill the 1s orbital. Now for something like oxygen, it needs to fill both the s and p sublevels in order to have a full valence electron shell. So for oxygen, the valence electron configuration will be 2s2 and 2p4. We don't include the 1s2 because that's not part of the valence electrons. And remember, valence electrons involves the electrons that have the highest principal energy level, and in this case, the highest principal energy level for oxygen will be 2. And oxygen wants a full octet. In other words, it wants a full valence electron shell, so it wants this to become 2s2, 2p6. So it needs to add 2 electrons. Oxygen can achieve this by just getting 2 electrons and becoming oxide, but it can also achieve this by sharing electrons. So in this example, oxygen is sharing its electrons with this oxygen, and as you notice, both oxygens now have 8 electrons after each oxygen decided to share 2 electrons to the other oxygen. So now both of these oxygen atoms have the electron configuration it wants, and they are both officially stable, and that's why oxygen forms double bonds. Now what about nitrogen? Well, it's the same case here. Nitrogen has a valence electron configuration of 2s2, 2p3, and it needs 3 more electrons to become 2s2, 2p6. And remember, this is 8 electrons, and by having 8 electrons, it fully covers the shell for the 2s and the 2p sublevels, and these are the valence electron sublevels, so they're officially stable once nitrogen gets 3 electrons. Now, it can achieve this by becoming an anion and becoming N3-, which is nitride, or it could share electrons. So in this picture, the 2 nitrogens are each sharing 3 electrons, and if I draw the circle again, you would notice that each nitrogen has 8 valence electrons now, and that matches 2s2, 2p6, and now both nitrogens are happy and stable. So that's why atoms form bonds, and let's now move on to the next topic. So let's now take a look at this diagram. It tells us the electric potential energy level of 2 atoms when they get closer and closer to each other. Since potential energy, in our case for 2 atoms, is the energy between 2 things when they are attracted to or repelled from each other, then it must follow that 2 things that are not attracted to each other or repelling each other, such as here, where the 2 atoms are not interacting, should have an electric potential energy of 0. However, as we decrease the distance between the 2 atoms, and in this diagram, decreasing the distance between the 2 atoms, also known as the internuclear distance, is when you go to the left. As you go to the left, the internuclear distance decreases, and when it decreases, something interesting happens. So, as you move toward the left, where the internuclear distance is decreasing, then you get proton-electron attractions, and when 2 atoms are getting closer, their electrons will naturally be attracted to maybe that proton in the nucleus there. And since we're looking at hydrogen, there's only 1 proton since the atomic number of hydrogen is 1. So these electrons will be attracted to the proton in hydrogen, and these electrons will be attracted to the proton in the other hydrogen, And in the end, the two atoms will be attracted to each other. And when they're attracted to each other, they're going to move closer and closer, as shown by these two arrows. And as a result, these proton-electron attractions lead to stability. And remember, when things are stable, they correspond to low energy. So for this example, the bonded HH atom is stable, first of all, because the 1s2 shells are both filled, and stability corresponds to low energy, which is why the energy of the bonded HH is less than the energy when they are separated, since when the two hydrogens are separated, they each have just one electron. And remember, hydrogen needs two electrons to be stable. So since it has one, then it won't be stable when they're alone. But when they come together, they will become more stable because each of them will now have two valence electrons, which fills the 1s2 orbital that the H needs to be stable. So let's clear two misconceptions. So the first misconception might be, oh, in this diagram you said it's hydrogen, but there are like 20 electrons surrounding it, so why is that? Well, in reality, there's only one electron surrounding the hydrogen, but I put a bunch of dots around the proton in order to show where the electron is most likely to be. So you can think of the dot as the place where the electron is most likely to be. And notice how as you get farther and farther away from the nucleus, there are less and less yellow dots, and that just tells you that as you get farther away, there's a lower chance of finding the electron in hydrogen. So the electrons that I'm drawing around this proton over here is just showing the probability density. It's showing where that one electron is most likely to be. So don't confuse the yellow dots for electrons. And the only time where I'll put one electron is when I'm drawing the Lewis dot diagram, such as here. And yeah, these yellow dots are representing probability density, so just remember that. And the second misconception might be, well, why does lower energy correspond to stability? Well, you can think of it this way. Things that have lower energy are more chill, and because they are more chill and calm, they are more stable. Meanwhile, something that has a higher energy is more chaotic and rampant, and that's why they have a lower stability. So now that we've talked about high and low stability, let's talk about what happens when the atoms get too close. So in this diagram, the two H's are kind of mushed together. They're like pretty close to each other. And when they get close enough, the proton and the other proton will start to repel each other, and you get something called a proton-proton repulsion. And when they're repelling each other, you know that they don't want to be near each other. And because they don't want to be near each other, it takes energy in order to put them together, which is why you get from a low energy state such as here to a higher energy state such as here, because you need to put energy into the system in order to keep the two protons together at this state. And because it's unstable at that state, it means that you need to put a lot of energy in order to keep this as it is, since it's hard to keep it together. And the harder it is to keep something together, the more energy it takes. And that's why this hydrogen-hydrogen bond, when it gets too close, when the internuclear distance gets too small, then the repulsion will occur, and this will lead to the two atoms needing a lot of energy in order to, keep this close attraction stable. And remember, high energy means low stability, so this means that the two atoms being this close is not going to be stable because you have to put so much energy into it for it to work. So that's how this diagram works. And now let's look at something a little bit different. So if you move down the screen, you see that over here, there's something called a bond energy. Now the bond energy is the energy it takes to break this bond and return it to the state where they're separated. So in other words, this could be a reaction where the bonded HH is changed so that they are separated, and the energy it takes to separate them is the delta E, and it's a positive value, and this is known as the bond energy. Now, how do you exactly read this graph in order to get the bond energy? Well, if you think about it, this minimum here is the amount of energy that's stored in the bond between H and H. So if this H and H wants to go to the point where they don't have a bond with each other, that means that the energy here has to go all the way up here, where this is the energy when they're unbonded. So in other words, you're going from a bonded energy to an unbonded energy, and since the unbonded energy is higher in energy than the bonded, then that means that you have to put energy into here in order to get from here to here. And this difference in energy is called the bond energy. So that's a graphical representation of bond energy. So let's now look at one last thing. This will be about bond length. Now, bond length is the internuclear distance between two atoms that are bonded in the most stable, not bond, but way. So, where in the graph is the H and H most stable at? Well, remember, the most stable place is to be at the lowest energy. And at the lowest energy, that's where the HH bond is most stable. So, in nature, when we see some hydrogen gas, this bond here represents the most stable form of the bond, and the most stable form of the bond is when the bond has the lowest amount of energy, which is right here. So this is a representation of how the bond should look like, because the distance, or the internuclear distance that corresponds to this low energy, is the same thing as the distance between the two nuclei, and this distance d, you can think of it as the most ideal distance between two H's that want to bond. And at the lowest point in the graph, that d that corresponds to the lowest point will be the bond length, or the internuclear distance between the two nuclei, and that's where it's most stable, so that's the bond length. So you might have been confused at the beginning, so let me clarify some things about this graph once more. So over here, this is the portion of the graph where the proton-electron attractions are causing the energy to decrease, and this leads to stability. But if you look at this part of the graph is increasing, meaning that the two atoms are beginning to feel a proton-proton repulsion, and this decreases the stability between the bond, and it leads to a higher energy state, which is why, as you go to the left, eventually you'll get some positive values for the electric potential energy, and this just means that the two atoms are so close to each other that they are basically unstable, and they are in a very high energy state, since it takes a high energy state to maintain this attraction between the two atoms, even though they want to separate from each other so badly, as shown by these arrows. So I hope you learned a lot in this video, and I know things were not in order because I had to mention some things that I forgot to mention in the previous slide, but I'm sure that you were able to keep track of it, and I hope you learned a lot, and have a nice day.